Exercise set 1.1. The title is Systems of Linear Equations, 2 Variable. Manual solution using 1. Graphic approximation and 2. An algebraic method. Single point solutions. Here's the instructions for 1 through 12. For each system, A, is the system linear, 2 variables? If not, state this and explain the reason. If so, proceed to answer parts B, C, and D below. B. Provide a graphic approximation of the solution to the system. Be sure your graph meets the quality standards of our class. C. Provide an algebraic solution to the system. This solution will be exact. D. Assess the correctness of your entire solution. Exercise 1. Alright, let's examine this system here. The first equation, is the first equation linear? To be linear, you need to be able to be rewritten in the form ax plus by equals c, a and b not both 0. Or less formally, if the equation has only constant multiples of x and constant multiples of y and constants, it's linear. Well, that's the case here, so equation 1 is a linear equation. The second equation, just as written, it's in the form ax plus by equals c, and it's linear. So, for A, we can say, yes, this is a linear, by the way, x and y, 2 variables, 2 variable system. Okay, that puts us into part B, where we're going to try to provide a graphic approximation of the solution. To do that, we need to individually graph the solutions to each individual equation. So let's take this first equation here. Now, having said it's a linear equation, 2 variables, we know the graph will be a straight line. How about getting that that line graphed? Well, what kind of coordinate system would be convenient? I like to get the intercepts graphed when it's convenient, and it looks like that would be nice here, but I want to make sure that they fit on the graph. So I do a quickie little calculation to see what the x and y intercepts are. For x intercept, you can let y equals 0, just like that, and now the equation looks like 2x equals negative 5, x equals negative 5 halves. Okay, keep that in mind. Let x be 0. You can do it by just covering it over. And now you have negative 3y equals negative 5. So y would equal 5/3. Alright, that's a rather small number. Keep that in mind. The second equation, its graph will be a straight line. As far as intercepts go, if I let x be 0, y is equal to 4. If I let y be 0, 2x is 4, x is 2. Okay, I just kind of quickly go through that at first to see what kind of coordinate system I can put here, and it looks like a very simple one. X going from perhaps negative 5 to positive 5, and y doing the same should be sufficient to get everything we need to appear. Sometimes you make a mistake doing this and you have to draw a second graph, but it's okay. Okay, some principles of a good graph. A good graph needs to have its axes labeled, for one thing. And in this case, it's going to be x's on this axis and y's on this axis. A good graph needs to have the scaling defined. In this case, I'm going to choose each tick mark to be worth 1. So to convey that to the person reading, I just label any one tick mark on each axis So for instance, on the x-axis, I'll go 1, 2, 3, 4, 5 right there, and back the other way. 1, 2, 3, 4, -5. There, the x-axis is scaled. Same thing for the y-axis. 1, 2, 3, I'll say 4 right here, and -1, 2, 3, -4 there. Okay. Now, let's go back and this time be a little more careful and actually start graphing as we go along. As far as intercepts on this first equation goes, alright, let's see, let x be 0, and now the y is equal to 5/3. That's 1 2/3. That would be there. And I'm also going to use a red pen here because I'd like to have a contrasting color so that the graphs appear distinct from the coordinate system in the background. Secondly, let's get the x-intercept. So let y be 0, 2x is -5, x is -5/2, or -2.5. Right there. Alright, 2 points a fair distance apart, so I can get an accurate graph by connecting these two. Now, something else. The person looking at this graph needs to know what is this red line. So, we will label it with its corresponding equation. That is, this is the graph of the solutions to 2x minus 3y equal to -5. Alright, getting ready for the graph of the second equation. For this, another contrasting color, blue. Let's get the intercepts again. So if x is 0, y is 4. If y is 0, 2x is 4, x is 2. Okay, connect these 2 points. Now, what is this blue line? The blue line is the graph of the solutions to 2x plus y equals 4. Alright, now, what's our main goal in doing this graph? Well, we're trying to provide a graphic approximation to the solution to the system. The solution to a system is the point that is the intersection of all the individual graphs in the system. In this case, then, we could go right in here and identify this as being the approximate solution to the system. So, time for a big conclusion here. We can say the approximate solution is the x-coordinate, let's see, it looks like about 1, and the y-coordinate looks to be 2.3. So maybe we record something about like that. I want this in a prominent cloud because it is the conclusive statement that comes with having answered part A. You want your conclusive statement to kind of jump off the paper, not be buried in the background so anyone has to look hard to find it. Okay, so we have our graphic approximation. Now we can go ahead and go to part C. This is B here. Okay, let's go to part C, which is an algebraic solution. Let's rewrite the system. It's 2x minus 3y equals -5, and it's 2x plus y equals 4. Alright, this system is really well suited for something called an elimination method because there's 2x's in this first equation, 2x's in this second equation. It's really already prepared to go for an elimination. Let's see how that works. The basic idea is to, roughly speaking, take the first equation and subtract the second one from it. In this case, in other words, like so, 2x minus 2x is 0. Negative 3y minus y, that's negative 4y. Negative 5 subtract 4, that's negative 9. Now solve for the y. Y would be, well, 9/4. Now I stop here for a minute to see if I have got consistency with the graphic solution or the graphic approximation. Looking at the graph, as far as having a y being 9/4 goes, this does look consistent because our graphic approximation shows a y of about 2.3. Okay, so since this is looking pretty good, we're justified in continuing forward. And now we'll try to solve for the x. Okay, looks like the second equation here would be an easy way to come up with the x. If we rewrite the second equation using the y now known to be 9/4, we could have it look like 2x plus 9/4 equals 4. Okay, so then 2x would equal, well, let's see, 4 minus 9/4. 4 is 16/4. 16/4 minus 9/4. 7/4. Alright, so x itself would equal to, divide both sides by 2, 7/8. Looks like we are ready to say here that the solution is, and by the way, I should back up here a minute. When we have this x equal to 7/8, checking back to the graphics approximation, we noticed we had an x of about 1. That's nice, because 1 and 7/8 are pretty close to each other. Again, we're seeing that consistency. So we're ready to keep going. The solution is 7/8, and the y was 9/4. Okay, it's a conclusive statement. Prominent cloud. And now, even though we've already been doing it, it's time to check our overall solution. Here's where you want to see the consistency between the two solutions that we basically have, the graphic approximation and the algebra, which is exact. Okay, well, let's see what we have here. We had the graphic approximation was this. It was, we said, 1 and 2.3. The algebraic solution this was 7/8 and 9/4, which would be, let's see here, 0.875 and 2.25. Little mental arithmetic there. And we notice the 1 is rather close to 0.875, and the 2.3 very close to 2.25. So we are able to claim the graphic approximation and algebraic solution are consistent. That is, they both have a very similar conclusion. That gives us our check. That makes anyone reading this solution feel confident that it is indeed correct. And that means not only the algebra was correct, but the graph is also looking very good as well. Okay. Exercise number 3. Let's take a look at the system, decide if we think it's linear, two variables, or not. The first equation. This equation has the form ax plus by equals c. It's linear. Let's look at the second equation. It's got x here, but look at this, a minus y squared. Okay, this is a problem. you can't have a y squared in the equation and have it be linear anymore. This is going to disqualify this equation from being linear. Once one of the equations is nonlinear, the entire system is considered nonlinear. So, here in part A, no, this system is nonlinear. Now, we were supposed to give a reason. The instructions ask for a reason. Alright, so why is this? Well, we could say the second equation has a negative y squared term in it. Thus, the second equation is nonlinear. Therefore, the system is nonlinear. Alright, this was a rather thorough explanation to finish this question. Looks good. Exercise number 7. Let's see if we think this system is linear two variables or not. The first equation has the form ax plus by equals c. That's linear. The second equation has the form ax plus by equals c. It's linear too. Okay, we can answer part A. Yes, this is a linear system in two variables, x and y. Alright, this brings us then to be responsible for parts B, C, and D. Part B. Here we have our graphic approximation. Alright, let's see. Getting ready to graph all the equations of the system and then seek the intersection of all the individual graphs. We know there's going to be two straight lines here. Now, to make sure it fits on our coordinate system, I'm going to check out the intercepts in these cases and plan to have a coordinate system that will fit the intercepts. So, for instance, this first one, just a quick calculation. Let x be 0, y would be negative 4. Let x be 0, or y be 0 rather. Now x would become 16/3. That's 5 1/3. Okay, keep a note of that. Second equation, let's examine its intercepts just quickly. Let y be 0, x would become 3. Let x be 0, y would become 5. Alright, just that little quick calculation roughly tells us that a coordinate system with x going from negative 5 to positive 5 and y from negative 5 to positive 5 will pretty much fit everything we need to do on this. So let's sketch that. Let's see. Okay, part of good graphing is, first of all, to make sure each axis is always labeled. Alright, in this case, we'll have this being x's. This vertical axis will be y's. Alright, and we always want a scalar axis. Now, this has been thought through, and we decided to go 1 unit per centimeter. So 1, 2, 3, 4, 5. back. 1, 2, 3, 4, 5. There, the x-axis is scaled now, and I'll label this one with 4 and with a -4 there. Now the y-axis is scaled too, so always make sure you're scaling the axes so that it's exactly clear how much each tick mark is worth. Okay, now we can begin graphing. Let's see. To graph the first equation, let's go back and let's really get those intercepts and graph them this time. Now let's let x be 0, y would be -4. Okay, right there. Secondly, let y be 0, x would become 16/3. That's 5 1/3. That would be there. Okay, straight line to connect these 2 points. And what else shall we do? The person looking at this graph wants to know, what is this red line? So we communicate that. Right here, a little label with its corresponding equation. That is 3x minus 4y equals 16. Okay, and again, notice the contrasting color, red, makes this graph of the solutions stand out from the coordinate system. Now, time for a third contrasting color to graph the solutions of this equation. We know it's a straight line. Let's get those intercepts again. X is 0, 3y is 15, y is 5. Okay, there. Let's let y be 0. 5x is equal to 15. X is 3. Okay, there. Alright. A straight line to connect these 2 points we've graphed. And label this line here with its equation. That would be the 5x plus 3y equals 15. Alright, now the most important purpose of what we've done so far is to try to approximate the solution to the system. What about that? Alright, we know graphically it's the intersection of all the graphs. Looks right about there. Okay, so now we can come in here and say that the approximate solution is, okay, what about that x-coordinate? You can even come back with your ruler to assist you if you want to be even more careful. So it looks like, let's see, maybe 3.9, and the y-coordinate looks to be about -1.1. Okay, this is a conclusive statement to this question here, this part A. So I'm going to put that in a prominent cloud. Part of communicating is to have the important information jump off the paper so no one has to look around to see what is the important conclusion here. Alright, so there we are with that. Now, time to go to an algebraic solution. Okay, let's go to the algebraic solution, part C. Rewrite the system here. 3x minus 4y equals 16. 5x plus 3y equals 15. Okay, let's see. This time the elimination is not already prepared for us. We got to do a little work. We have a couple choices. We could make it so that the x will eliminate, or the y's. Either way. Let's see here. Maybe we choose to get the x's to eliminate. So that means we're looking at the 3x and 5x. 3 and 5, common multiple would be 15. So multiply this first equation, both sides by 5. That would be 15x minus 20y equaling 2. Let's see, 5 by 16, 80. Okay, the second equation, multiply both sides by 3. That would give us 15x plus 9y equaling 45. Alright, now we can go here. We can take this first equation, subtract the second from it. 15x minus 15x, 0. Negative 20y minus 9y. Okay, negative 29y. 80 minus 45, 35. Alright, solving for y, we'd have a y equal to a negative 35 over 29. Alright, now this can be a little disturbing, such a strange fraction. Let's think about it though. Let's compare it to what we had graphically. Now 35 over 29, let's see, that would be a negative 1, and then we have 6/29, that's almost 6/30, that's about 0.2. This is about equal to negative 1.2. Okay, so if we look back at our graphic approximation, you know what? The y-coordinate was about negative 1.1. So this is actually looking pretty reasonable. Alright, let's continue, see what happens to our corresponding x at this rate here. We could take either of these equations here. I suppose this one may be easiest. It's close. Okay, so taking the first equation, we've got 3x. We'll need to add 4y to both sides. Now, y is a negative 35 over 29. Okay, so we've got indeed some arithmetic to deal with here. 4 and 29, no cancellations there. We need to go into the world of 29ths. Let's get 16 written as some 29ths. Sometimes you gotta do a little scratch work. So let's see, 16 times 29 up here. 6 by 9, 54. 5, 6 by 2, 12. 17. 9, 2, 4, 16, 4. Okay, so this is then 464 plus a negative minus 4 by 35. 140 over 29. Okay, what's this give us then? This would come down to, let's see, 324. Which is one step away from getting there. X itself would be, got to divide both sides by 3 here, and that would give us, 3 goes into 324 evenly, 1 and 08 over 29. Okay, now what about this number here? Let's just do a little bit of old-fashioned arithmetic here. If we take 29 and put it into 108, let's see, it goes in, let's see, 1, 2, 3 times. That would be 87, giving us, okay, now we got 210. We're looking at about 7 times there. Okay, think of that graphic approximation. That graphic approximation, we'll go back, look, it is about 3.9 for x coordinate. So, as strange as this may look, thanks to the graphic solution, graphic approximation, that actually seems pretty reasonable. So, let's record our answer here. The solution is 108 over 29, and the y-coordinate, we had a negative 35 over 29. Okay, let's get a cloud around that. Now, part D. We've already been talking about this, but now we formalize it. The check on our work here. Okay, we have for our graphic approximation that was equal to, reviewing, that was 3.9, negative 1.1. The algebraic solution which was 108 over 29, comma, negative 35 over 29, which is about equal to 3.7 we had, and negative 1.2, which, if we compare there to there, there to there, both x's and y's are indeed consistent. Okay, so therefore the graphic approximation and the algebraic solution are consistent. Looks like a check, and don't be afraid of doing a little bit of good old-fashioned arithmetic to come up with a little bit tough of a solution like we got here. But because of the graph backing us up, we can feel confident this is looking pretty good. Okay. Exercise 11. Okay, let's decide if this is a system which is linear, two variables, or not. The first equation, 2x plus 3y equals 22, that has the form ax plus by equals c. That's linear. The second equation, couple problems here. A divided by x in this term, that's a nonlinear term. And there's a divided by y in this term, also a nonlinear term. It appears like a problem. Sometimes you can do an algebraic manipulation and transform the equation into an ax plus by equals c, but it doesn't look too hopeful here. Let's try something. Maybe we decide we will clear this x and this y all at once, multiply both sides by x times y. Alright, so if you did that, and this side by x times y, the result would be, let's see, the x's cancel here. Here's 6y plus the y's cancel here. Here's 8x. And then, x times y. A cross product term. You can't have that in an equation and have it be linear either. Okay, so we made a little effort. Nevertheless, the conclusion is unchanged. And we simply must say here for A, no. This system is nonlinear. And to cite a reason, back to the original pair of equations, the second equation has a 6 divided by x term in it. That would be sufficient there. And thus nonlinear. Therefore, the system is described as being nonlinear. Okay. And that's it. When the systems are nonlinear, we are not solving them in this exercise 1.1. Exercise 13. Alright, this one has independent instructions of all the previous 12. Let's read what it says here. A line with the equation y equals ax plus b passes through the points 11 halves, negative 8, and negative 4 -3. Find a and b by using some system of equations. Okay, well, first, I always kind of like to have a graphic approximation of things, and it helps to make the solution more convincing to everybody reading it if I have that as well. So, first I like to kind of draw a picture of the situation and see what we think. Let's see, what kind of coordinate system will fit these points here? 11 halves, -8, -4, -3. Okay, we do seem to need a fair amount of negative y-axis, and the x's are kind of about 4 or 5 units to the right or left. Alright, let's try maybe something like so. Let's see. I want to make this about like this. Okay. As always, I want to label and scale the axes. X is here, Y is here. I'm planning to scale one tick mark as 1 unit, so 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. More right. Okay. Let's see these 2 points. I get a contrasting color. 11 halves, -8. Okay. Graphing a point is kind of out in the midst of the coordinate system here. Maybe a ruler assistance can help. So I've got the y at -8, and now I want to go 5.5 centimeters to the right. There. Okay. 11 halves, -8. Right there. The second point, -4, -3. Okay, again I can ruler assist myself here. I'll get a ruler on -3 and then come over 1, 2, 3, 4 units. There we go. Now, the line will be about like so. Okay, let's see. We can do a little work on this problem off of our graph. Again, we haven't gotten to really solving it the way we're supposed to yet, but we could do a little work here. We have this line. How about its slope? We could come here and say the slope could be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. In this case here, we can go with, this is our sub 2 point, here's our sub 1 point, so we would have -8 minus -3 means +3 over x sub 2, 11 halves, minus x sub 1, +4, and this will give us, let's see, there's a -5 over 4 halves, rather this is 4, so 8 halves, and 11 halves, that's 19 halves. To divide by 19 halves is to multiply by 2/19. Okay, about -10/19 for the slope. And by the way, even a little graphic check on this is available, because as we look at this line, we at least agree that it has a negative slope, because as you ride on the line from left to right, you are going downhill, and it's not as steep as a 45-degree angle, so its slope should not be a -1, but rather something between 0 and -1, which it is at -10/19. Okay, a second thing here. Oh, by the way, let's finish up the why is it nice to have a slope approximation here is, well, this is actually a slope calculation. This is not actually an approximation. We used very specific numbers here. So this is actually furthermore going to equal RA, because we know this form of the equation, y equals ax plus b, a represents the slope, b represents a y-intercept. So this is equal to a. Maybe we give this a little cloud. It's not really our true answer yet. We haven't gotten to that just yet, but a little something. Secondly, right here, now this looks like about negative 5.1, and that is what b appears to be approximately. The squiggly equal sign means about equal to negative 5.1. Alright, so maybe I have that, and I should maybe identify all of this here as graphic, approximation, just to get ourselves thinking about this problem. Okay, now let's go to our actual solution. Because the problem actually specifies how we are to solve it. Use some system of equations. Alright, so we start off with this idea that we have a y equals ax plus b for the form of the equation. Now, if 11 halves negative 8 is on the graph, that implies that 11 halves negative 8 must be a solution to the equation. Meaning, when 11 halves is substituted for x, negative 8 is substituted for y, it must make it true. Okay, so this then implies that negative 8 is equal to a times 11 halves plus b. Okay, now let's use the same kind of thinking. In other words, let's take advantage of this negative 4 and negative 3 being on the graph. Okay, well that tells us that negative 4, negative 3 is a solution to y equals ax plus b, and that implies an error like this. In math, a lot of times means this implies that, and that's what it does mean here. This implies that put negative 4 for x, negative 3 for y, must make this equation true. This makes this say negative 3 is equal to a times negative 4 plus b. Okay, now to keep more organized, maybe we should label this as equation 1. Label this here as equation 2. Now, if we look things over for a minute here, we notice that equation 1 and equation 2 constitute a linear system. Okay, observe equation 1 and equation 2 constitute a linear system. Okay, let's record it here, maybe in a more standard form. So this could be written as 11 halves a plus b equal to negative 8, and we can rewrite equation 2 as negative 4a plus b is equal to negative 3. Okay, this is well prepared for an elimination, right? We have just a single b in each equation. we can take the first equation, subtract the second from it, roughly speaking. So 11 halves minus a negative, which is add 4. Add 4 means to add 8 halves. That brings us up to 19 halves A, B minus B, 0, equals to negative 8 minus 3, minus a negative 3, which would be negative 8 plus 3, making this negative 5. Okay, getting A solved for, multiply both sides by 2/19. Before we go further, check back to our graphic approximation where actually A, the slope, was solved for exactly, not even approximate, and we have an agreement right there. So that's good to see. We can confidently proceed forward to try to get the B. Let's go to, I suppose, this second equation here. From the second equation, we would have B is equal to negative 3. Let's add 4A to both sides. 4, we now know what A is. It's negative 10/19. Okay. Alright, this will be, looks like we're going to have to go to 19ths here. So, negative 3 multiplied by 19 over 19. That will be negative, let's see, 57. And then adding this negative, that's basically a subtraction, 40 over 19. This gives us, let's see, negative 97 over 19. Alright, stop here for a moment and notice the negative 97 over 19. Well, this is a little more negative than negative 5. Negative 5 would be negative 95 over 19. Okay, so this is a little more negative than negative 5, which is consistent with our graphic approximation of the B, negative 5.1. So despite the, non-simple fractions panning out here, this is actually looking pretty good because it's consistent with our graphic approximation that we started off with. So let's proceed to then fully answer this question. We could say that A is equal to negative 10/19 and B is equal to negative 97/19. That's the main conclusion of this question. And we might point out, as we've been mentioning, as our check on all this, we have that the graphic approximation had A equal to negative 10/19 and B equal to negative 5.1 is consistent with the algebraic A equals to minus 10/19 and B equaling negative 97 over 19. Very close to negative 5.1. And these two are just plain equal, which they should be. Looks great. Okay, very good.